So, finally starting our last chapter of the semester and of the year. So, we're going to be talking about nuclear chemistry. We're going to look at two types of nuclear reactions. The first type is radioactive decay, which is the most prevalent and at least what we're most used to around. And it is a process where a nucleus spontaneously disintegrates and gives off radiation when it does. When it disintegrates, it's something that is unstable. So when it disintegrates, it tries to go back to be something more stable, and it gives off radiation in the process. The other type of reaction is nuclear bombardment reactions. That's where we can get energy out of a reaction. So this is what happens often in a nuclear reactor or on the sun or in atomic weapons. And this is a reaction where a nucleus is bombarded by other nuclei or nuclear particles, and then energy is released. Okay, so the phenomenon of radioactivity was first discovered in 1896 by Becquerel. I believe he had his uranium salts near some photographic paper, and he saw this cloudiness on the paper and didn't know what it was from. So he was the first to see that that they gave off something that was detectable and gave off this radiation. When the radiation was tested, it turned out to have three types of radiation: alpha, beta, and gamma rays, which we'll talk about in just a second. So alpha rays are positively charged. So they bend away from a positive plate of a magnet or an electric plate, and so they're positively charged. And it turns out that they are made up of 2 protons and 2 neutrons. So they're really a helium nuclei without the electrons. So 2 protons and 2 neutrons. Beta rays or beta particles are bend opposite of an alpha, so that means they have a negative charge, and it turns out that they are made up of high-speed electrons, so they're the same size and shape and weight of an electron. So alpha particles are much larger than beta particles. And then gamma rays are actually unaffected by any kind of magnetic or electrical field, so they are neutral. They are a form of electromagnetic radiation that's similar to X-rays, but higher in energy and shorter in wavelength, but they are similar, like it says, to X-rays, so and similar in how they can be dangerous. All right, so this is just a picture of the uranium metal, and the radiation is sent through some electric plates, and you can see that the beta particles are attracted to the positive side, the alpha particles are attracted to the negative side, and the gamma particle or the gamma ray goes straight through, so they are neutral. So the first thing we want to be able to do is to write a nuclear equation. And so this is a symbolic representation of a nuclear reaction, and we're going to be using nuclide symbols. So we talked about nuclide symbols way back at the beginning of the year when we talked about protons, neutrons, and electrons. So here's an example of a nuclide symbol for uranium-238. So the symbol of the element is written on the right, and then on the upper left is the mass number, and that is the total number of protons plus neutrons, and then on the bottom left we write the atomic number, which is the number of protons. And I want to warn you again that the mass number and the atomic mass on the periodic table are related to each other, but they're not exactly the same thing. So when we're writing a nuclide symbol, we're talking about one particular atom with a particular number of protons and neutrons. So your top number should always be a whole number. It may be the same as the atomic mass on the periodic table, but notice that most of the time the atomic masses are a decimal. And so remember that the atomic mass on the periodic table is an average. It's a weighted average of all the nuclei, all the nucleus, all the nuclides, all the different isotopes of the different elements that are out there. So for example, uranium is 238, but if you look on the periodic table, it's 238.03. So you wouldn't put 238.03. And in fact, there could be other uraniums out there. There could be uranium 235. There could be uranium 239. There could be any different numbers of them. So just as a review, if this uranium has 92 protons, then it has 238 minus 92, or 146 neutrons. So the number of neutrons can change for the different isotopes. The number on the periodic table is an average of all of them, but when we write a nuclide symbol, we're talking about one particular atom that has a particular number of protons and a particular number of neutrons. Okay, so here is an example of a nuclear equation. So uranium-238 decays by alpha particles. So you can see it's lost an alpha particle, which we could represent as a helium nucleus. So helium has 2 protons and 2 neutrons. So the bottom number is a 2 and the top number is 4, 2 plus 2. And so uranium has broken apart into an alpha particle, and the other particle is thorium. So this is an example of a nuclear equation. We're going to talk about it just a little bit more, and how we would write this and how we would balance it in just a minute. So when we're writing a nuclear equation, reactants and products can be represented with their nuclide symbol, like we just saw on the previous slide. And then other particles are given certain symbols that you should be familiar with. So a proton, which of course is 1 proton and no neutrons, can be given the symbol on the right, 1 proton and 1 total mass number, protons plus neutrons. Or because 1 proton is hydrogen, you can write it with the hydrogen symbol 1 and 1. So of course 1 proton, and then the top is the total of protons plus neutrons. 1 plus 0 is 1. The neutron can be written like this. The neutron is a little n. It has no protons, so 0 on the bottom, and of course 1 on the top because it has a total of 1 proton plus neutrons. An electron can be written as it is on the right-hand side, where with the E symbol. Of course, it has no mass at all, so 0 on the top number, and it's not totally intuitive, but it has -1 proton, so we put the -1, and you see when we balance these equations how it'll work out. That you just need to remember that the electron has a -1 as its bottom number. Since electrons are also beta particles, you can also write it as with a beta symbol, with the -1 on the bottom and a 0 on the top. Either one of these are correct. So if you're writing it, either one would be correct. You can put either one, but you should be familiar with both of them because they may show up somewhere. So you should know what they both are. A positron is a particle that is identical to an electron in size and mass, except it has a positive charge rather than a negative charge. So the symbols are exactly the same as an electron, except for the bottom number is a positive. And of course, it doesn't really have a proton, but you'll see when they balance out that that's the most appropriate way to write them. A gamma photon has no mass or charge, and so that's the gamma symbol, and it has 0 protons and 0 neutrons, and so for emphasis you can put the 2 zeros. You don't always have to put the zeros. The gamma by itself is also correct. And then, as we saw on the previous slide, alpha particle is a particle that has 2 protons and 2 neutrons. So you can write it on the left because it is a helium nucleus, which has 2 protons and 2 neutrons. Or sometimes you'll see it written as it is on the right, where you'll see the alpha symbol with 2, 4. Or you might just see the alpha symbol, but you need to know that it has 2 protons and 2 neutrons. All right, so the main thing about a nuclear equation is that the total charge is conserved during a nuclear reaction. So although one compound will change to another, the total charge is conserved. What that means is that the sum of the subscripts for the products must equal the sum of the subscripts for the reactant. So all those bottom numbers have to be equal across the arrow. Now, the total number of nucleons being protons and neutrons, the total number is conserved during a nuclear reaction. And so what that means is that the sum of the superscripts for the products must equal the sum of the superscripts for the reactants. So if you know all the reactants and products but one of them, you can identify the missing particle by subtracting, and so you just have to know what the total is on both sides of the equations. If you'll know the total on one side, and you can find the total on the other side by filling in what's missing. So I think we'll do an example right here. So, technetium-99 is a radioactive isotope. Each nucleus decays by emitting a beta particle. So what is the product of the nucleus? All right, so here's the nuclear equation. So technetium-99, so we know that 99 is the mass number because it's given to us. If we just said technetium, we wouldn't know what the top number was because, of course, the periodic table is the average. But technetium-99 is one isotope that has 43 protons and a total mass of 99. So it has 99 minus 43, or 56 neutrons. Okay, it's going to decay by a beta radiation or beta particle. So one of the products is a beta particle. So you can see that on the right hand side. One of the products is a beta particle. And it doesn't matter which order you write them in, whether you write the beta particle first. It's just like A plus B equals B plus A. You can write them in any order. So what is the product nucleus? So we want to know what is X. What will technetium turn into when it goes through a beta process? So the main thing you want to keep in mind is that the total bottom numbers have to equal each other on the on either side of the arrow, and the total top numbers have to equal each other on either side of the arrow. So you can think of the arrow as sort of an equal sign. So if you look at the superscripts, you can say, okay, 99 on the left, whatever A is, it has to plus 0 has to equal 99. So of course A is 99. So that one was pretty simple. So the mass number for X has to be 99 as well because it didn't lose any particles. Now for the subscripts, you can see that 43 is on the left. What does Z have to be in order for the two sides to be equal? So Z minus 1 has to equal 43, so that means Z has to equal 44. So now we know what it is. It's element 44, which is ruthenium. So now we can identify the whole new symbol. It's X is replaced by ruthenium. The bottom number Z is 44. The top number is 99. So when technetium reacts, it turns into ruthenium and it shoots off a beta particle. It does seem odd. It is actually converting from one element to another element, and that is one of the that is what radioactivity is. It's changing elements. Now, so you should understand that when it's emitting a beta particle, the beta particle is a product, and so that's why we sort of we put that on the right hand side. And I think we'll do a few more examples of these as we go on. All right, so what makes something what makes it radioactive? It's due to the nuclear force. So it's sort of the balance of protons and neutrons in the nucleus. So the nuclear force is a strong force of attraction between the nucleons, so the protons and the neutrons, that acts at a very, very, very short distance. So in general, this force can more than compensate for the fact that positive charges are really, really close to each other. So it's this force that is not really what we can imagine, but they're able to be held close together in a stable nucleus. There's actually, and we're not going to get too much into this, they believe there's a shell model of the nucleus similar to electron shells, so that different protons are at different levels in the nucleus. And it turns out that nuclei with a certain number of protons and neutrons appear to be very stable. So it's kind of like the number of neutrons to proton ratio has to be just right, and it'll be stable. So these numbers are called magic numbers, and they are numbers of nuclear particles that kind of complete the shell. They're not the same as electrons, 8, 18, 32, but they're similar. So because nuclear forces differ from electrical forces, these numbers are not the same. So like I said, they're not 8, 2, 8, 18, etc. So it turns out that some of the magic numbers for protons are 2, 8, again, but 20, 28, 50, and 82. These are some of the most stable elements with these number of protons. And then for neutrons, here's some similar magic numbers, 126 included. And then there's also certain stability for pairs of protons and pairs of neutrons, so certain correct numbers of certain numbers of protons and neutrons. This is not anything you have to remember, but it just shows how many stable isotopes have an even number of protons and an even number of neutrons. So 59% of all the stable isotopes that are present on Earth have an even number of protons and an even number of neutrons. So odd is kind of not as common. Another 20% have an even number of protons but an odd number of neutrons. Only 19% has an odd number of protons and an even number of neutrons, and then only about 1% has an odd number of protons and an odd number of neutrons. So that's just kind of interesting. If you plot each stable nuclei on a graph of protons versus neutrons, we end up seeing, we'll see it in just a second, most of the stable nuclei fall in a certain region, or it's called the band of stability. So this band of stability is a region in which stable nuclides lie, and let's look at it. So here, notice that we've got number of protons plotted on the x-axis, number of neutrons plotted on the y-axis. And actually, you notice that near the beginning, a smaller number of nuclei, and you've probably recognized this already, things like carbon, nitrogen, oxygen. A lot of the smaller nuclei, actually, the number of protons and neutrons are often the same. You know, carbon 12 has 6 protons and 6 neutrons, and nitrogen 14 has 7 protons and 7 neutrons. Oxygen has 8 protons and 8 neutrons, so the most common stable nuclei. But then you notice that as you get bigger and bigger, the more protons you have, then suddenly you have more neutrons than protons. And so you can see this band of stability kind of goes off to the left of this red line where protons equal neutrons. We'll talk more about this band of stability in a minute. But all the stable nuclei exist in this yellow band of stability. So in fact, no stable nuclides are known with atomic numbers greater than 83. So everything above 83 is radioactive. On the other hand, all elements with atomic numbers equal to 83 or less have at least one stable nuclide. The exceptions are technetium, which is atomic number 43, and promethium, which is atomic number 61. And if you look at the periodic table, you see sometimes it depends on which periodic table you're looking at, but a lot of times the technetium, not yours particularly, but actually you see parentheses around the atomic number for promethium. Anything that is actually synthetically prepared and doesn't exist on Earth have that. They're either outlined or they're atomic numbers in parentheses or something like that. So let's talk a little bit more about the 6 common types of radioactive decay. The first one we're going to look at is alpha emission or alpha decay. Sometimes you'll see it written as an alpha symbol. Sometimes you'll see it written as the helium symbol with 2,4. So it is a helium nucleus or an alpha particle which is emitted from an unstable nucleus. So here's your nucleus, and then you see the alpha particle being emitted from it. Here's an example of alpha decay. Radium 226, so you can see it has 88 protons and a total mass number of 226. You can see on the right hand side that alpha decay, alpha particle is being given off, 2 protons and a total of 4 mass number. And so what is the other product that's given off? Well, you have to balance it out. So it's radon with 86 protons and a mass number of 222 will balance this equation. Also, sometimes you'll see instead of helium, you'll see the alpha particle written like that. So the second type is beta emission, and you can see sometimes it's written as a beta, the Greek symbol beta, or sometimes you'll see it beta with a negative afterwards. And it is the emission of a high-speed electron. Now it looks just like an electron, it's the same size, but it comes out of the nucleus. So it's not the same as grabbing an electron from an atom, from the outside of an atom is shot from the nucleus of the atom. So in fact, this is equivalent to changing a neutron to a proton. So you can see the balanced equation. A neutron, which has 0 protons and 1 mass number, converts to a proton, which has 1 proton and 1 mass number. So it's the same size, but it's changed to a positive particle. And so to balance the charge off, an electron or beta particle is shot out of the nucleus. And so you can see now why the beta particle is written with a -1 on the bottom, because it balances out this equation. So an example of radioactive decay is carbon-14. Carbon-14 has 6 protons and 8 neutrons, so a total of mass of 14. If it gives off a beta particle as one of its products, the other product that is formed is nitrogen-14. Sometimes you'll see the beta particle written as an electron, either way, beta or electron. So a third type of radioactive decay is positron emission. And like we talked about, a positron particle is the opposite of an electron. It's the same size and mass, but it's got a positive charge rather than negative. So sometimes you'll see a beta particle, a positron particle abbreviated with the beta symbol with a positive, or as we've seen before, with the positive one on the bottom and a 0 on the top. And so again, this is equivalent to the conversion of a proton to a neutron. So the proton, 1 proton and one total protons plus neutrons, will convert to a neutron. And again, to balance out the charges, a positron has to be emitted. So here's an example of positron emission, the radioactive decay of technetium-95. So you can see technetium with 43 protons and a total mass number of 95. The mass number hasn't changed, but the number of protons has gone down 1 to become molybdenum, and then a positron particle is emitted. A fourth type of radioactive decay is something called electron capture. You might see it abbreviated as EC. This one's a little bit different from the others because a particle is not actually emitted, but it is similar to a positron particle in effect. So it is actually the nucleus is unstable, so it will grab or capture one of the low-lying electrons that are circling it. When that happens, the spot where that electron is no longer there, so some of the other electrons from higher orbitals will start to fall down to that lower level, and when it does, energy and radiation is sent off. So you can see here this picture is sort of showing it. So again, just like a positron particle, it changes a proton to a neutron. It just looks a little bit different because this time a proton grabs an electron and becomes a neutron. So it's balanced a little bit, but the same process happens. A proton turns into a neutron. An example of this, and now you can see because an electron is being added to the nucleus, it's on the left-hand side of the equation. So potassium 40 will decay by electron capture. It grabs an electron, so an electron now is a reactant. It grabs it, and you can see that 19 minus 1 gives you 18, 40 plus 0 gives you 40, and so the new product is argon 40. So another radioactive decay that we have talked about already is called gamma emission with the gamma symbol. And this is just when an excited nucleus will shoot some energy out of the nucleus that has a wavelength of about 10 to the minus 12th meter. So it's on the is close to an X-ray in size. So in this case you have this excited state called a metastable state. You don't actually change any particle to anything else, but it's like it's unstable, so it's metastable, and then this excited state emits this gamma photon in order to come down to a lower energy state. So here's an example, and you see the little m. A metastable technetium-99 will decay to give us normal technetium-99 and a gamma particle, or no, it's not really a particle, a gamma photon will be emitted. Okay, one last type of radioactive decay is called spontaneous fission. This is when an unstable nuclei, which is very heavy, so it only happens with the heavier nuclei, so if it's got mass number greater than 89, it'll split into two lighter nuclei. And then oftentimes energy and sometimes neutrons are released. This is an example of uranium-236, which undergoes spontaneous fission. So uranium-236 will decay, in this case, to yttrium and iodine, and 4 neutrons are given off. What you want to notice again is that the total numbers are the same. So 53 plus 39 gives you 92. 96 plus 136 plus 4. Notice because there's 4 neutrons, you have to multiply that one. So 96 plus 136 plus 4 gives you 236. And I will have to say that this is not something like the other ones you knew, okay, a beta particle, you could figure out what the other product was. You couldn't predict what this would be. So if this were an equation that I would give you, probably just one of the products would be missing, and you would have to tell me what was left by balancing out the numbers. So you couldn't necessarily predict that uranium would split to yttrium and iodine. It might split to other things very similarly sized. All right, so this is just a nice little chart that kind of summarizes everything. So you've got alpha emission, which gives off alpha particles. Beta emission gives off beta particles. Positron gives off a positron. Electron capture really just gives off X-rays, and then the gamma emission. You can also see here equivalent process. So beta emission is equivalent to a neutron changing to a proton, and both positron and electron capture are equivalent to a proton turning into a neutron. You can see the resulting nuclear change. For an alpha emission, the atomic number will go down by 2 and the mass number will go down by 4. In beta emission, the atomic number will go up by 1, but the mass number doesn't change. For both positron and electron, the atomic number will go down by 1 and the mass doesn't change. And then for gamma emission, neither atomic number or mass number changes. And then we'll talk about this again in just a second, but the usual nuclear condition. So alpha emission tends to happen if the atomic number is greater than 83. The beta emission is if the neutron to proton ratio is too large, and then positron and electron capture is if the neutron to atomic number ratio is too small. So it turns out that it's these nuclides outside the band of stability that are radioactive. And these aren't hard and fast rules, but these are just the kind of the guidelines that we're going to use. So nuclides to the left of the band actually have more neutrons than they need for a stable nucleus, so that neutron to proton ratio is too large. So they will tend to decay by beta emission because it reduces this neutron to proton ratio, because neutrons are converted to protons, and so it reduces the neutron to proton ratio. So nuclides to the right-hand side of the band have a neutron to proton ratio that is too small. That's needed for a stable nucleus. And so these nuclides will tend to decay by either positron emission or electron capture. You really can't predict, at this point, we can't really predict which one. So you would just say either or. You would say both, either positron or electron capture. And the reason why is because it converts proton to neutron, and so you're increasing that neutron to proton ratio. And then the very heavy elements, especially those with atomic number greater than 83, will tend to decay by alpha emission. So we saw this already. Here's the band of stability, and now you can see this was already written on it. To the left of the band of stability tends to be beta emission. To the right tends to be electron capture and or positron emission. And then you can see that alpha emission generally happens with nuclides greater than 83. So that would be up there. So sometimes it's hard to predict what's going to happen, and we're not always 100% correct, but we're just going to kind of give some guidelines as to figure out what kind of radiation or if radiation will occur at all. So let's predict the expected type of radioactive decay for each of the following radioactive nuclides. So again, not hard and fast rules, but these are the guidelines I want you to follow. So let's look at calcium-47. So if you look on the periodic table, the atomic weight of calcium is 40.1. So what that means is that the average stable calcium is 40. Now they're not all 40, but remember that we said that the number on the periodic table is closest to the most stable nuclide, or the most abundant. So if it's the most abundant, it's probably the most stable. So we expect calcium-40 to be a stable isotope. So then what we can do is say, well, calcium-47 has a much bigger mass number than the stable isotope. So that puts it to the left of the band of stability. So we would expect that this would decay by beta emission. So for aluminum, the atomic weight for aluminum is 27. So we expect aluminum-27 to be the most abundant and a stable isotope. So aluminum-25 has a mass less than that. So we would expect this to decay by positron emission or electron capture. Now, if something is greater than 83, I would just have you predict that it would go by alpha emission. So although radioactivity has been, changes one element to another element, and that's a natural process, in 1919, Ernest Rutherford discovered that you can change one nucleus to another. So they didn't really understand it till then. And so transmutation is the change of one element to another by intentionally bombarding it with a nuclear particle. So either one nuclei or a neutron or alpha particle, something like that. So Rutherford used radioactive alpha particles to bombard nitrogen, and so nitrogen-14 was bombarded with alpha particles, and he was able to convert that to oxygen-17, and a proton was also emitted. So protons were ejected. So then this sort of came more and more of this work. So James Chadwick was one that it was sort of the first one to discover the neutron. So neutrons weren't even discovered until here. So it was because of radioactive reactions that the discovery of the neutron was found. So Chadwick bombarded beryllium with alpha particles. So they were known to exist, but alpha particles bombarded beryllium. It turned that into carbon-12, and a neutral particle that was before now not known was emitted. So that was the discovery of the neutron. So how can you can't just sort of throw alpha particles or neutrons at something and expect them to react. You actually have to accelerate them at very, very high speeds in order for them to bombard one nucleus to affect another nucleus. So the way that that happens is you may have heard of a accelerator, a particle accelerator. A cyclotron is one type of particle accelerator where you take the source, so like say it was an alpha particle, it comes out the center and there's this magnetic field and it spins the particle, and so as it spins it gets faster and faster and faster. So when it comes out it's going very, very fast enough in order to bombard another particle. So they can't just throw it like a softball. You have to hit them really fast. And so a cyclotron or a particle accelerator, this is just one type of accelerator, gets these particles going extremely fast so that they can collide with other particles. So anything above 92 is uranium, and uranium is actually the largest naturally occurring element. So it's naturally occurring. You can find it on Earth. Anything above 93 is all man-made. And so actually the first transuranium element was produced at the University of California at Berkeley, and it was produced an isotope of element 93 by bombarding uranium with neutrons. And so they were able to slip a neutron or hit it with a neutron and convert it to element 93, which again is only man-made, and that is neptunium. And then other work has yielded other elements all the way up to 118. So anything above 92 has all been man-made, and it's all been done with bombardment kind of reactions.